and then we move to the last speaker, and it will be Andrii Goriachko from Taras Shevchenko National University of Kyiv. Are you here, Andrii?
Yeah. Okay. So yes. So I'm starting. Yes. So today I will talk about graphene on germanium 111. And it's about growth, electronic and structural properties, and mostly important about perspective applications. Next. Currently there are a lot of proposals to utilize this system where graphene contacts germanium substrate for numerous perspective electronic devices with various unique properties. For example, the most common electronic device, transistor, is already being considered that it can gain a lot if graphene is utilized within its structure. And there are actually quite a lot of proposals. I will just show you a couple of several very recent papers, like the ones that you see here on the screen. So here you see the heterojunction transistor. It's a bipolar transistor which contains graphene as a base electrode. And here on top, on the right, you can actually see the structure of this transistor. Next one. And there are also various different varieties of transistors that you can make. For example, hot electron transistors, the structure of which and the photo of which you can also see on the screen. It is also a very recent publication of the authors that you see here. And in these terms, you can actually, if you look at the analogy in the vacuum electronics, then for instance, in this case, you can consider graphene so that it can be viewed as playing the same role as a metal grid in the vacuum triad. Next, please. Then graphene also makes a perfect passivation of the germanium surface, which can be applied to create stable heterostructure devices, stable in terms of the influences of various environmental factors. Next, please. And of course, since we all know that graphene is a very nice conductor, we can also imagine a Schottky junction, a Schottky barrier. And there were also proposals and very recent publications about the interface between germanium and the single layer graphene, which is a Schottky junction, the bent diagram of which you can also see on the screen. And also it is important that in this context, you can, graphene here can be viewed as a metal electrode, which is just one atom thick, but is also optically transparent, which can be of great importance. You can utilize it in creating various, for instance, photoelectric sensors as a transparent electrode. Next, please. So this is the type of the deposition process, which is applied quite often by many researchers. Graphene is usually grown on copper substrate. Then it is attached to the PMMA film and detached from the substrate and then transferred onto germanium. And once the PMMA is dissolved, you are basically left with graphene on germanium substrate. However, of course, such procedures, these are procedures at ambient conditions or wet chemistry procedures. And of course, the germanium substrate is not atomically clean under the graphene layer in this case. Next, please. So what I have studied so far, but without synchrotron radiation, just with small lab-based techniques like scanning tunneling microscopy and Auger electron spectroscopy, was the CVD type, chemical vapor deposition type of graphene germanium interfaces. in which case, of course, germanium substrate is first achieved in the atomically clean state. And then, as you can see here, there are STM images and corresponding Auger spectra showing two situations: atomically clean germanium substrate that is on top, and germanium substrate partially covered by graphene. And this is a spectrum and an image on the bottom. So basically here you see that there is a substrate with atomically flat terraces separated by single atomic steps, and some of them are covered by a certain structure, which you can see in a detail in the inset. And as it turned out, this is how the graphene flakes look like under the scanning tunneling microscope in ultra-high vacuum. Next, please. So if we zoom in, we again can compare the atomically clean germanium substrate that is on the left and partially covered by graphene flakes that is in the middle. And of course, there is no such thing as absolutely atomically pure substrate or whatever, any kind of material in nature. So there are always some kind of impurities. Carbon is a very common impurity when you prepare the semiconductor surface like silicon or germanium. And you can see here that we consider that the surface is atomically clean, but still that means it's clean to a certain extent. There are some impurities, they can still be present on the surface. And for instance, on the left side, you can see that when there are very small amount of carbon atoms, then they just form the C letter, as you can see in the lower part of the image, which tells us that this is carbon. But when there are a lot of carbon atoms, then they form a continuous graphene layer, as you can see in the middle image on the slide now. And so basically this is how it looks like also in the STM with atomic resolution at high magnification. Next, please. Also, I have made experiments at different, although low electron energies, that is obtaining spectrum microscopic scanning tunneling microscopy experiment or observation. And here we indeed have been able to confirm that, yes, the graphene layer can act as a sort of analogy to the grid of the vacuum triad. So in some situations, for some electron energies, they can tunnel through, or some of them just tunnel into it. And we have been able to tell this difference by means of being able or not being able of observing the substrate germanium atoms in the STM images of the germanium substrate covered by the graphene layer. Next, please. And so by this, I actually want to conclude saying that this system, graphene on germanium, is a very interesting system with a lot of perspective applications, but it was not investigated using the synchrotron light. And from the previous slides, I think it is obvious that the issues that can be investigated using the synchrotron-based techniques would be, for instance, lateral homogeneity of the coverage, because a lot of images that I have shown you, they show non-uniform coverage of graphene substrate, of germanium substrate by graphene. So there are covered areas, and not uncovered areas. And of course, chemical bonding at the interface will also be very interesting, also in terms of the depth resolution, which is, of course, very easily doable by means of the synchrotron-based photoelectron spectroscopy, for example, or adsorption spectroscopy. So it would be extremely interesting to see, to distinguish the bonding just within the very few layers, or within the upper layer atomic layer of this system, of this interface. But of course, it will require also spatial resolution at the nanoscale to differentiate between the covered and uncovered areas of the germanium substrate. So this is also where we can benefit from the synchrotron-based techniques. And of course, ultraviolet photoelectron spectroscopy, as you can see, these two images, where a big graphene flake is situated on the germanium substrate, again, partially covered. It has the STM image which changes in real time. That is, it differs when you observe it from one image to the other. And that means that the electronic structure and perhaps the crystalline structure as well at the interface is changing in the real time. So observing this would require also the temporal resolution in the maybe seconds or sub-seconds range. And so I think by this I will conclude my talk, and thank you for your attention, and I will be happy to answer any of your questions.
Thank you, Andrii. Okay, it is the last talk. I think the next session will not be long. Therefore, in principle, you can ask a question. If waiting for questions from others, okay. Better Yaroslav. Yaroslav, please ask questions.
Thank you, Andrii. Yeah, thank you for nice talk. Obviously, my question then would be: could you please be more specific? Unless maybe I overheard or I missed it. If you would be offered now, to go and do any kind of analysis, like a synchrotron-based type of analysis, what you would go for? Yeah, what would be, the most useful for you? What do you think to better kind of understand this system and to, yeah?
Okay, I think what I would be interested to do right away would be the special resolved photoelectron spectroscopy. That is where I can see the chemical bonding information, and also specifically at the uppermost layer, so that is between carbon atoms, between carbon atoms and germanium atoms. So this is the most obvious thing. We will need a resolution, as you can see, for instance, from the image now on the screen. We would need maybe also the spatial resolution. That's why I talk about spectral microscopy, photoelectron spectral microscopy, within maybe tens of nanometers to differentiate, to see the mapping. Because if we are speaking about the applications of such graphene layers on germanium in electronic devices, and obviously we need to achieve the situation when there is a homogeneous, absolutely uniform coverage without any such holes, as you can see here on the screen, where there's uncovered germanium. So this should not be the case. And therefore, the growth conditions have to be checked during such experiments. So, as I say, I will repeat, spatial resolved X-ray photoelectron spectroscopy. That would be my first choice.
Okay, thank you. Yeah, makes sense. Yeah.
Okay.
I would say that it would be interesting. Sorry, you didn't finish yet. Yeah.
No, I said that it's all makes sense, and yeah, I said that he definitely should apply them. Yeah, should try to get some time.
Okay. Thank you.
My impression, if speaking about the beamline which we are planning, that the diffraction with localized beam would be interesting for you, but now applying for ARPES, angular resolved photoemission spectroscopy, to Solaris, I think Eva could actually not help, but say answer your requirements. But you should just apply for beam time.
Okay, thank you.
I wanted to ask some maybe naive questions. I have an opportunity to switch it. Yeah. What could you just explain what is this? What makes this honeycomb structure and what are these white dots? because I'm lost.
Yes, I understand. When graphene contacts germanium in atomically clean state, then we have a very close contact of two lattices. One is the surface lattice of germanium, another of graphene, and they have different
superstructure.
Yes, yeah, sure. So this is a kind of a so as a result, the upper layer, the graphene layer, becomes corrugated. Yeah, it's basically like when you are trying to fit a carpet, to put the carpet on the floor of the room, but the size, for instance, the size of the carpet is larger than the room, so it will have to be corrugated in order to fit.
Yeah.
So this is a kind of a phenomenon that we are dealing, and it is best seen in the empty electronic states, and that is the leftmost and uppermost image that you can see on the screen now. So you can see the height corrugation. But then at other energies of the tunneling electrons, it can be that some of them tunnel into the graphene because there are electronic states available for this. And in other situations, for other energies, they tunnel right into the substrate because there are no electronic states, or the probability of tunneling is too low. And these two phenomena, they give rise to all other images that you can see on the, and it's indeed so that it's easy to get lost here. However, maybe the uppermost and rightmost image, the image D, explains the point. At image D, you can see there are some remaining brighter spots. These are some remaining spots within the graphene layer, which are actually imaged in the STM. And in between them, there are a lot of smaller circles, and these are just the germanium atoms. So we have checked that the periodicity, the distance, the interatomic distance in between them is in D, image D. The interatomic distance between them is just typical for the germanium substrate. So that means in this case, we just see through the graphene layer very nicely. And all the other images are situations in between. Yeah. Also, there are at plus volts. So if you have positive voltage, then these are the empty electronic states of the sample. That is of the substrate and of the graphene together. And negative voltages, for example, F and G, occupied states.
I understand, yeah, that the dots which you see on D, it is just okay. This is ordered, yeah. Either it is graphene or it is beneath graphene. It is another question. And black stuff, it is just superstructure. It is superstructure like Moir pattern, yeah.
Yes, sure. You always see some remaining.
But on G, this random, let's say, random white dots. What are they?
Well, it's a very nice question, up to the point. Thank you very much. Let me be honest. The honest answer, we don't know yet. To do this, one would need to do extensive theoretical modeling of the STM image formation for the known, geometrically known crystalline structure of the interface. However, my proposal, so my idea is that this in image G, these brighter dots, these are still carbon atoms of the graphene layer. However, as you can see, the carbon atoms within the graphene layer becomes non-equivalent. So some of them are brighter, some of them are almost not visible. And also, it is proposed, but not proven, that the reason behind this is that the layer of germanium atoms just beneath the graphene is actually mobile at room temperature. So that means there are a lot of vacancies, and as a result, there are a lot of configurations of the germanium atoms in the topmost germanium layer that they can assume, and by this they change the local geometrical structure of the interface and the electronic and the local electronic structure also as a result. And as a result, some of the carbon atoms in the occupied states become brighter. So they start to have more local electronic density of occupied states due to this. Okay, this is my answer.
Okay. There is such a hypothesis. I understood. Thank you. More questions to the last speaker? Okay, then I should thanks all the speakers of this session again. I will stop sharing.
Thank you.